Oh, very good evening or very good afternoon, rather. Welcome back to the class. As we have already started going for B tree, which is one of the most important and useful data structure. So last class, we have talked about the B tree, the node structure. The correspondingly, we have also discussed the insertion searching issues. And more importantly, we also talked of disk read or related issues, etc. And how T is decided, the degree of the battery, how it will be helpful or how it will be used. This is what we have talked the last time. Today, what we are going to do is insertion, which is extremely useful and interesting operation. And then tomorrow we are going to do deletion. We will talk of insertion for initial around 30-35 minutes, and last 10 minutes we will talk of the programming aspect also. So programming aspect, of course, relatively not so easy, but that also for those who really enjoy programming, that also we will cover up and see how to do that. For deletion, programming is not given in the book also, but those who are interested, they will try deletion also. But for today, let's focus on insertion. So in case of a B tree, insertion we have to do, let's think of having some normal B tree. For the time being, I assume T equal to 3. So I'm taking the example which book has used more or less so that you can revise from the book also whenever needed. So if I have a root node where this is my root node, there are 4 key values in this. So 4 key values will obviously mean there are going to be 5 children. Let's talk of this children. Let's assume you have here A, C, D. Say assume here for this, I have got JK here. For this, I have got NO. For P, you have got, let's say, R, S, T, and V. And for this, we have got Y. And assume all these are leaves. So no further downwards. Simple tree taken, simple B tree. T equal to sorry. T equal to 3 means minimum 2 keys will always be there in every node, and maximum 5 keys will be there everywhere. Of course, with the root, this condition will not be of the minimum not applicable, but for the time being, we have minimum 2 keys, maximum 5 keys in every node, including root. Now, let's say think of any insertion. First aim will be that aim not to do it in non-leaf node. That will be my first attempt. Why? Obviously, if I think, let's say, for example, if I say I want to insert E. Now, if you want to insert E, one way could be that here also I can have E. And because the root has, this node has one space available, 5 keys can be there. I have here 4 keys. E could come here. But I should not do this, because if E comes here, this will create extra pointer requirement also. If I say get here E, G, M, P, X, then I require 6 children. 5 values, 6 children. These children do exist definitely. Corresponding to before G, say some values existed, but for these two, ACD could go one side. For example, this could have been for ACD. But what about under this? What will you link? So you don't have extra node available, so you will never prefer to do. Similarly, extra leaf also cannot be created. Extra nodes beyond leaf, yeah, at next level to leaf also will never be possible. Next level to leaf, that will also mean we should never do that, because say if you think that yes, somewhere here I will include something E here, that will mean leaves start at this level. And if leaves start at this level, other leaves were earlier on the higher level. So I'm going to create problems for myself. So I will never do that in any situation. So ideally speaking, I will say never have this. I have never this. And this remains normal. I will never prefer this anywhere. And this all I'm not going to use in any way. So all that will be useless for me. And I will never prefer to do anything like this. That will straight away mean that my aim will be always to have insertion to be done in the leaf nodes only. First aim will be insert in leaf node. If not possible, then I'll think of a solution. But otherwise, in a leaf node only, things will become easy. So I want to insert E. I will start from here. I have to find out under which leaf it will reach. So obviously this will never be done like this. From here, G versus E compared. Immediately I come to know that I have to follow this pointer. Come to this node. This is already a leaf. So in leaf, insert in node, let's say X. And in X, how to insert? Always use insertion sort, because you have to create a space for putting the proper value. In this case, of course, X node actually means nothing, but here I have got some keys field. In keys field at index 1, I have got A, then I have C, then D. So this is index 3. Total 5 indexes are available. This and this are free available. So I can easily put E. So effectively means I am able to add E here. Let's say now next step. So this I did 1. Second I do, let's say insert, say U. Insert U. Again, I will start from the root. Aim will be always do in the leaf only. So for that, I have to start from the root. Root, I will start. Let's note down, start from root and find the children. So from root node, I will start. There are multiple values. Effectively using the searching logic, I will find G versus U. U is greater. So somewhere towards the right to come. M versus U. M versus U. U is still bigger, means still go further. P versus U. P is still smaller than U. So still further. X. When I reach to X, U is less than X. That means this pointer to be followed. Before X, the pointer is just values less than X. U is just less than X. Greater than P has been already established. So this value is greater than P and less than X. So U is supposed to come here. Here I have got R, S, T, V. Again, using insertion sort, effectively what you will do is initially you have V here. So your V will be shifted here. Space will be created here. U will be inserted here. And ultimately, I will have U coming. So earlier, V was at index 4 in the key field. Now we will reach to index 5 and I'm able to insert U at the right place. Now think of, let's say, insert B. Insert B. Of course, I will start from here. I will start from this. Currently compare with the root. G straight away tells B is less than G, means this pointer to be followed. This is a leaf node. C, D, E will be shifted towards the right. Space will be created in between and A, B, C, D, E will become. Similarly, let's say I have some more values to be inserted which create no problem. I can do that. So some more insertions may work, but now let's think that I want to insert Q. So I take new situation. What I have got is at present I have G, M, E, X, And under this pointer, for the time being, I have RSTUV. I said insert Q. From here, you will compare, keep on comparing, keep on finding. Ultimately, you find that yes, this is child I pointer, which direction you are supposed to go. Q is supposed to come here. Here there are 5 values already. Full. This node is full. And Q is supposed to come. So now I get a problem. So now I have to think of situations like this, where leaf is full, where to put. Any other arrangement will require some special logic, so we have to think. But Q has to come here, and this doesn't have a space. So the solution will be, ultimately, this node will be split. Split current node can be one solution. I'm writing can be. Later, I will just define what we will do. Can be one solution. What that will mean? That this node has full values. So I will say current node is your RSTUV. I will out of this create extra node, new node, malloc. In this, I will say divide these values around median. Divide values or divide keys around median. Not only keys, if child also, if exist, and children also, if exist. Means what? Around median, it will be divided or split. Around median means around this value. Remember, this node has always odd number of keys guaranteedly, because it exactly had 2t minus 1 keys. So around key t, we will divide. Means values before t will remain in the current node. Values after t will be copied. If a pointers existed, these will also copied. So all this is copied here. And t will be a value which will be shifted upwards. T will come into this particular parent node. So T will be, I'll say value T, not exactly this T, I'll say value T which I have here, which I mean this T. This is at index, of course, key T, by the way, same value, will be now shifted into the root node or into the parent. What does that mean? Earlier it has GMPX. So I will actually get GMP and T is supposed to be here. So T will reach here. By adding this, extra child pointer will also be available. And that is the advantage of this. So with P, the pointer was going to the current node, which earlier had RSTUV, but now it will have RST. And this will get to the new node which we have created just now. That will be linked via this extra pointer. X current pointer is already okay, same as earlier. So this was already existing. This pointer already existing. This pointer already existing. This pointer already existing. So that means effectively now what my total tree becomes GMPTX. Before G, I have here say A, B, C, D, E. Now here I have got JK. Here I get NO. Here I get RS. Here I get UV. And here the already Ys. So this is the after splitting. After splitting, this happens. So this works well, can be a good solution, and we are able to still do, but there is one problem. What is the problem? Say you were at node X, where X means you were at RSTUV. Now from there, you want this T value to be shifted into parent. But how will you reach to parent? I don't have a parent link available at all. So how will I go to parent? First problem. Secondly, a bigger problem than having a parent. Maybe you can say store parent link also in each node. So you can have a parent link also in each node. Can be a solution. Yes, can be, not a big problem. But still there is a second problem which is more problematic. Extra disk read will be needed for reading a parent again. Because you will go back to parent might not be in the RAM. So reading a parent node will now require disk read extra. And we last time also said disk read is very slow. We want this never to be done. We want to have a minimum disk read. So we will not prefer to go from child back to parent, or maybe even multiple parents. मान लीजिए parent भी भर गया और ऊपर जाना पड़ेगा. How long will you go? Every time going will mean extra disk read. Of course, write also क्योंकि data change होगा. But fine, write करना ही पड़ेगा. This is must automatically. So कभी भी करना पड़ता, write तो करना ही पड़ेगा. But extra disk read needed. Why I am saying extra? Initially, you read the parent, that reading was must, and you did that perfectly fine. No issue, that was needed. Then you came to child I node, you came to X, that is child. This also reading needed, obviously. From here, from X, now you are supposed to go back to parent. This is an extra reading. When parent was read, at that time have not handled such problem, and now I get extra readings. So to avoid this, the solution comes, we will always go downwards only, never go upwards. Everything will be done in a single pass only. Before going to any node, any child node, I will say, or downwards, which I say downwards, ensure that it is non-full. Non-full, or it indirectly means split in advance while staying at the parent itself. I'm staying at parent only, and still I will do the splitting. So I say I will not split the current node, rather I will split the current child. Means what? When I was at this node GMPX, as soon as I came to know that I'm supposed to go to this node direction, even if it has downward children, first I will say, if I am going to some child I, if child I is full, split it. Split it first. Even if it might not require insertion immediately, but I will say split. Why? At split time, median can be brought into current node, into my current node, without disk access, without extra disk read. Why? I am already at the current node which has GMPX. So if this is my current node is still this one. I will say before I reach to child, before I recursively go to lower level, first I will say split the child. So staying current node here itself, do it like this. Current node is still this. Do all splitting, etc. And now saying once you have split, in current node T has also been added, and without any disk access it will get extra done. Of course, write also to be done, but write is not a issue. Write, disk write will be needed and that will be done. But now I say insert Q will be attempted now. Insert Q said that go towards the down. Before going down, I split this current node. I have to insert Q. So I'll find out whether insertion is here or here needed. I come to know that Q will be inserted in this. So I will say fine. I will be effectively shifting this, creating a space by shifting this using insertion sort. Insertion sort logic will be applied and I have got QRS here. So now what my node structure becomes, I have got GMPTX. Here I have got, let's say, A, B, C, D, E. And here I have got correspondingly JK. Here I have got correspondingly NO. Here I have got with P, after this I have got QRS. Here I have got UV. Here I have got WZ. Let's say now I say insert L. Insert L. Insert L when attempted. So again, as you could think that I will start from root, find out the proper pointer. Yes, so connection is re-established. Let me just reshare the screen. Connection has been reconnected. I'll just have the screen sharing done. So let me share my screen. Screen sharing done. And now I'm back to my screen. The connection was reset. I have to just wait for a few seconds. Yes. So now I say insert L. You could think that I will start comparing and reach to this node. But no. Won't go directly to JK. Before that, we said rule is split any node which is full, even if it doesn't require any node in advance, if full. And this rule is applicable on every node going downwards. Root you started, start from root is what we did, but immediately starting from root is full. So root is full will mean root will be split. How root will be split? With the same logic. Median will get shifted up and this node will split into two. But where to shift median? Shift median where? There is no higher parent. Parent doesn't exist. Will mean extra level will be created. So this is how tree depth will increase. So this will actually mean now I will split. This will become GM. This will become TX. Extra road created. P will go there because that is empty. And linking like this done. Root is created. So root will change. Changed root now. So this change will happen and now this link. Rest everything is same. These pointers are same. total 6 pointers earlier existed. You can see I had pointer child 1, child 2, child 3. Earlier this was child 4, child 5, child 6. Still 6 children existed. Now also they will still continue. Child 1, child 2, child 3. And earlier they were called as 4, 5, 6. But now that will become this node's child 1, child 2, child 3. Still total nodes are same. So this extra splitting will happen. So root is a split, and node extra created. So extra root or above node created, extra level created. So this is how my height will increase. Height will increase through this process. And extra node created in this case is not in advance, because beyond earlier to root nothing existed. No extra disk access needed because this node never existed. So no extra disk read needed. It's a new created node. Malloc will be done, data will be assigned, linking will be done. But because it node never existed, so it's not an extra disk access. But in case of a root, ultimately it has to be done. So for all other nodes except root, we will split in advance before going down. On the root itself, if root splits, extra node will be created. But there are many advantages. Now, extra node created means root can have maximum 5 keys. Of course, we have the rule of not having root minimum keys. So at present, one value only, one key only, but that is allowed. In root, we are allowed to have one key also, need not be minimum 2 minus t minus 1 keys. So, but now there is a future insertion easy. Future too many insertions will be possible now. Many insertions will happen without much problem, without extra level or extra split. Why? You can easily see root can have 5 values. So I can have here total 5 values. So a lot of scope. This node also can have 5 keys, lot of scope available. This node also can have 5 keys, lot of scope, and each of them having 5 keys. Earlier, my total leaves could have been, total leaves possible were like I had GMP TX at most. This could be the best case. So leaves which possible were maximum 6. Now, how many leaves will be possible? Effectively, 36 leaves will be possible, because P is root. Here I can have maximum 5 values. 5 values will mean maximum 6 children. 6 children will mean here again maximum 5 values. In each of these nodes, maximum 5 values, each of them further having 6 pointers. So each of them can have 6 children now. 6 children by each of them. This is child while I1 to child 6. Each of this 6 can have further 6 children. So total 36 leaves will be possible. So now my tree has a future expansion without difficulty. I have here P, I have here GM, I have here TX, and this also can grow a lot. This also can grow a lot. Accordingly, the lot of growth in each of them will be possible. For the time being, this had JK. Now I will become this as a JKL and like. So earlier when I started to insert L, I said insert L, although insert L was going to be in this node, but this indirectly forced the split of the root, and now JKL comes without touching this node, without touching this node, without insertion anywhere, but advanced splitting was done. And the Change is, for example, sometimes later this node becomes full. If I am going downwards in any of them, I will split this before going down. So from pay, if I come here and if it has got 5 keys, before going down, I will split this. Split will mean something to come here and etc. So advanced splitting ensures all insertion will happen in a single pass. And a single pass will be downwards and minimum disk read will happen. So that is the advantage. So this is what we mean by insertion logic. Any doubts? You are welcome. Otherwise, insertion process we have completed. Now comes the implementation logic. So for implementation, I will implement, or coding part I will implement in 3 parts. Coding. First I say, initially I will say I have an insert routine where root will be sent to me and the value to be inserted, let's say k. What it will return, we will decide, but its purpose will be root level split if needed to be handled. Only this, because all other works of insertion will require recursion. Recursively, we will go down, down, down. So at this level, first I will say, if root is full. So root is full will mean I will have new root created. That will be assigned equal to, let's say, root or whatever you say. Later, of course, I will write return root so that root changes for the future. So I must return from here the B tree star node or whatever node structure I have done, struct B tree star. So that node returned value, changed root is returned. In other cases, root will never change. So if root is full, I will create a root. Then I have to do all that splitting and then insertion of the middle value, median value at the root. That also I will do in a simple manner. What I will say, I will create a new root and keep it empty. Consider its child 1 as the current node, for example, gmptx, and then I will say, so I will say new root arrow child 1 equal to current root, whichever root variable I am given is that. Why I am doing this? After this, I am going to call a simple function which I call at a split child, that roots, new roots, a split child is to be done, and which child? Child number 1. So this means child 1 of new root to be split. Why I am writing like this? Advantage is split child will be needed many times. Split child will be a routine function which will write extra function which will be needed multiple times. So instead of rewriting the whole code here, I use the same function split child to do . So I said that we are able to have the split child called, and that helped me as an extra function, and we are able to have this added. Advantage is that yes, this function can be reused. Once it is done, now I will effectively be sure that the node is not full. So I will call a special function which I call it as an insert in a non-full node, starting from the new root, obviously. So now I can say the new root's corresponding child is guaranteedly non-full. So this call will guaranteedly work. On the other hand, if root was not full, if a root is not full, again it means node is guaranteedly having some space where I can fit in. So again, insert non-full will be called. So effectively that means I have insert non-full into the current root node value k being called. So the advantage of this function being either I will be inserting into a non-full, either insertion is a non-full. So that will mean I have the corresponding call to a non-full function, or full meant split will be done first and then call insertion in non-full. So in both cases, insertion in non-full will be called as a separate function, and a split function will be another called split child. So in both cases, now my original root, this insert function will be just for the root without any looping, etc. And either I call this function or I call first split and then this function. So effectively, what I now need is one function I need is insert non-full, and of course other function I will need is going to be split child. So let's go one by one. Insert into a non-full, whatever parameters. Ultimately, let's say I have got some node x and some value k. So guaranteedly it means x is non-full. I am coming to this function call from insert function. So x is non-full. K is to be inserted. So first case, if x is leaf, x is a leaf means guaranteedly k can be inserted and there is a space available. So effectively you will start I equal to x arrow n, and then backward wise you will keep on traversing and shifting. Effectively something like insertion sort. So I will say k to be inserted using insertion sort. And because all pointers are null, so child pointers are null, nothing special to be done. K will be inserted without anything. Of course, n to be updated, n to be incremented or updated. That all trivial values you can do. But if it is not full, if it is not leaf, non-leaf will mean I have to find out the child pointer. So obviously I will start from the I equal to 1, make some while loop for searching, etc., etc. Find the child pointer, find the ith pointer, effectively ith child pointer in which insertion is to be tried. Because I have to go to some child direction. Insertion is to be attempted. Attempted, I am saying, because in that node again you find another ith child and go in that direction. To be attempted. So all this can be recursive. So ultimately you will have a while loop, you will find child I. So now you know I have got a child I pointer. So effectively x arrow child I is to be used. Yes, this can be a recursive call, but before going to that, recursively possible, but before going to that, we will ensure that it is non-full. So I will check if this child I is full or not. If child I is full, so again, full will mean I have to split the corresponding child. So split child function will be again helpful to me. So split child of x, ith child of x to be split. This call I will generate. And once split, now I will be again calling insert non-full recursively. Which one? X is a child somewhere in within the x we have to insert either to the ith child or to the x arrow ith or I plus 1, because extra node will be created. I don't know which of these node will be used for the insertion. So ith or I plus 1th child, and within that we have to insert the corresponding value that is guaranteedly non-full. So recursive call can work. On the other hand, so if it is full, good enough, else. So if this is not full, I can simply say insert non-full into this corresponding child, this child further recursively. I can call that. So X arrow child I effectively to be done. And within this child I, K to be inserted. Yes, but in both these cases, before I say split child or before I say insert, there will be a disk read needed. Obviously, I need disk read. After split, a disk write will be also needed. That is, we must know. And in this case, obviously, read will be needed. So this is an extra time, but we should know this will be needed. Going to the last module, we are saying split child. So split child function will be called by some routine X saying that ith child to be split, whatever data type I need. Effectively, it means X arrow child I is to be split. And guaranteedly it is full. It is full. Child I is full. Of course, why I am doing it from X? Because staying on to the X, the median value of the child I will come to the X, so that will be possible without requiring extra disk access. So now effectively this means this is my X. Somewhere this child I is there. This is guaranteedly full. So it has got 5 keys. If a T is a 3, so I have got correspondingly 5 keys and maybe 6 pointers also. So there are 6 pointers also if it was non-leaf. So it is PTR, or I'll say child 1 to child 6. All these are available. So what I will do, say I assume, let's say ith child variable I will take. Ith child is effectively X arrow child I. So this is effectively the new node. For example, it has got certain values, say A, B, C, D, E, and maybe certain pointers, if at all. So I say this is my pointer ith child, temporary variable I have taken. I will create first of all a new node. So first step, create or malloc new node. So this becomes a new node available. Now in this, I will say copy certain keys. Which keys? Obviously, T plus 1 to 2T minus 1 keys of ith child. That ith child node is there into this new node. And where I will store? Into this obviously key 1 to T minus 1, because this is a new node. So effectively this means these two values will come here as a D and E at index 1, at index 2. Similarly, if children exist, they are also to be copied. So effectively, child T plus 1 up to 2T, because one child is extra. So these many children to be copied from ith child node into new node. Mainly this work. So effectively these node pointers will be also copied. Then next step will be obviously the median to be inserted into X. So median means effectively in the ith child, the key of T, because the T exactly is this one, T is a 3. So this is guaranteedly index this. This is a median. This key T to be inserted. Inserted using insertion sort, of course, so that there is a proper space made available in insertion sort in X. Of course, using insertion sort. So that will mean that somewhere at, let's say, jth position, this will get added into X, say jth position. So somewhere this is J, here I will get value C. This C copied. If a C is copied at jth position, then effectively X arrow child J plus 1 will be pointing to new node, because that node is extra. So effectively this link will come to this particular, I repeat, this link will come to this node. This pointer is already existing. This pointer was already here. That effectively means that this pointer was already okay. And this is new pointer, new child. This will come. And then final step will be update n, etc. Update leaf status for new node. One thing. And of course, n to be updated for X also, for ith child also, and for new node also. Why I am saying? For X, n increases plus 1. For ith child, n becomes exactly t minus 1. For new child also, it will become exactly t minus 1. Previous n is different. Now, updation of the n will be new. So that n will be updated. So more or less, this will be the logic. Without going into more details, now you can practice this doing programming, and hopefully you should be able to do this. So don't worry if you are not able to do it in a single go. Aim should be that you should be trying insertion logic and implementation, and good students will be able to make it most of this. Average students can try and nothing to bother if you are not able. At least the clarity of insertion should be there, and you should be able to insert based on the given data as and when needed. Thank you. Stop.